Hello. So today we are going to talk about Newton's third law. This is a pretty short lesson because it just goes over action and reaction forces. So Newton's third law states that for every action there's an equal but opposite reaction. So what that means is that forces always come in pairs. Any applied force will come in a pair. So what I mean by this, if you look in the bottom left-hand corner here where we have the hammer pushing down on the nail. So where the hammer obviously is applying the force to the nail, which is forcing the nail further into the wood. But the reason why the hammer kind of bounces back up from that is that the nail is also applying a reactionary force back to the hammer. So whatever force is being applied via the hammer, an equal but opposite reaction force will be applied from the nail to the hammer. Same idea here with this person on a skateboard pushing off of the wall. So you have an action force of the person pushing against the wall, and then the wall gives an equal but opposite reaction. So that's why the person pushes away from the wall. So you applied pressure to the wall, but the wall pushed you back and propelled you forward. So this video clip, I am not going to play it on here, but it is entertaining, definitely. So if you would like to watch that, it's kind of funny. There's just a bunch of people like running into each other using exercise balls and they go flying. But what I wanted you guys to pay attention to with this is how does the mass of the person and the speed that they were moving at affect the force. So do you get a greater reactionary force on the person with the smaller mass? Does it matter? And then you should have a pretty clear view that the reactionary forces are opposite. So some of these people run right into each other. The reactionary forces act on themselves and they go flying backwards. So like I said, you can watch that or not watch it, but what happens if you hit your desk with your hand? So if you push down on your desk or you hit your desk. Sorry about that. I got cut off here for a second. Someone had popped in my room. So what happens if you hit your desk with your hand? If you really slap your desk with your hand, you're going to feel that. So you have applied a force to the desk, obviously, and it has withstood your force and given you a reactionary force back. So that's why your hand would hurt. So if you hit the wall, your hand's going to hurt because the wall technically is hitting you back. I mean, obviously the wall is not going to reach out and slap you, but it's applying the same force you applied to it back to your hand. Okay, so Newton's third law, we know that all force pairs are going to be equal but opposite. It's the same idea as normal force with gravity, so we've kind of touched on that before. We'll get into normal force a little bit more next lesson, but all force pairs will be equal, but in opposite directions. The only caveat to that is if there is a head-on collision, the force is doubled due to a double action force. So if you have two vehicles that run straight into each other, they're both accelerating toward one another, and they both have an action force, the reaction force will be applied to both of them, because if the car on the left applies a reaction force to the car on the right, the car on the left also has its reaction force plus the force that the car on the left was applying. So you have double the forces. So in that case, if there's a head-on collision and you're trying to find the net force in order to calculate some other variable, you would include that force but double. So some examples I'll go through here. First one, you have a 100-kilogram hockey player checks an 85-kilogram player with a force of 65 newtons. So we have the two hockey players. This is your 85-kilogram player, and you have your 100-kilogram player. So the 85-kilogram player is providing an action force of 65 newtons, and then since he's receiving the action force of 65 newtons, I should say, because the 100-kilogram hockey player ran into him. So in this situation, you have the smaller person is standing still, he's stationary. The larger person ran into him. So the action force is being applied to the 85-kilogram person, and then the 100-kilogram person also gets the reaction force. So even though they're applying a force to another object, they are going to receive that reaction force. And notice that it is equal in magnitude but opposite in direction. Another example could be that you lean against a wall with a force of 25 newtons. So you're not applying a lot of force, you're just kind of leaning up against the wall. So your body is applying a force, an action force of 25 newtons to the wall, but the wall is also giving you the reaction force. So the wall is applying a force of 25 newtons back on you, which is why you're not accelerating through the wall. You're not falling through the wall. Another example is between the ground and yourself as you walk. So as you walk, your foot is applying an action force to the ground, and the ground is applying a reaction force back up to your foot. This is why you can push off the ground. This is also the same reason why if you're walking in mud or really soft sand or something like that, you don't get as much reaction force from that because it absorbs it. So if you're walking across the hard surface, you're going to get an equal but opposite reaction force from whatever action force that you applied. So if you think about it also as like running versus walking, when you're running, you're forcing your foot down with a pretty great velocity. So you're forcing your foot down, you're applying a greater force to the ground, and in return, the ground is giving you that reactionary force, which helps propel you forward. The last example is going to be the moon and the earth. So we have gravity acting between these two. Technically on this, you could say that the action and reaction forces could go either way because we know that the moon has its own gravity and then the earth has gravity also, obviously. So we do have an action force and then an equal but opposite reaction force for those. Okay, so let's do an example. So we have example 1 here. We have a 90 kilogram man, which is man 2. He's going to run into a 100 kilogram man, which is man 1, with a force of 85 newtons south. What force does the first man experience? And then we're going to calculate the acceleration of both men after the collision. So we have man 1 is red here. He's on the left, and man 2 is green. So man 2 is just running right into him. So what force does he experience? So man 2 is the first man because he's running into man 1. So man 2 will experience the equal but opposite reaction force. So if man 2 is running into man 1, he's applying a force to man 1, but he's also getting the same equal but opposite reactionary force. So if he's applying a force of 85 newtons south, he's going to get a reactionary force of 85 newtons north. The second part of this is to calculate the acceleration of both men after the collision. So we're going to have two separate parts to this problem because we have two different men with different masses. We're going to have to calculate their acceleration separately. So we know that we can calculate acceleration using this formula of net force divided by the mass. This is just reworked from force equals mass times acceleration. So we've just rearranged this basically. So here we have the acceleration of man 1. We know that man 1 is receiving a force of 85 newtons south, and man 1 is 100 kilograms. So if we have a net force of 85 newtons south, we're just assuming that there's no other forces acting on him. His acceleration will be 0.85 meters per second squared towards the south. For man 2, you're going to have the same magnitude of force, but in the opposite direction, divided by his mass. So he's going to have an 85 newtons north divided by 90 kilograms, which is going to give man 2 an acceleration of 0.94 meters per second squared north. Okay, so his reactionary force is pushing him north, which is opposite the direction that he's running. So man 2 is actually going to hit man 1, and according to our directions here, it's going to propel him backwards. So he's going to go back the way he came. So with this, we are going to do this Newton's third law lab. For the virtual students, you guys have these graphs already dropped into the lab, so you can analyze the same data that we're looking at in class. So what we did with these is we had a force sensor. We had two force sensors connected to one another, and we pulled them in opposite directions, and then we did that with a few different materials, holding them together, and then we did that with bumpers on them and pushing them together. So what we used was the LabQuest and all the Vernier equipment. So what we had here were the sensors. We had the force sensors of in the positive and negative direction, and then we get our graphs. So while this part doesn't apply to virtual. So while you guys are looking at these graphs here are what we're taking our data from. So basically your red line is one of the force sensors and your blue line is the other force sensor. So you will read these graphs as you go. So this part is just for in class. This doesn't apply to anyone probably watching this video. So try the lab. The lab is on Canvas, obviously, and like I said, all these graphs are dropped in so you can see the real data that we collected in class, the same as what we will collect in class. Give that a shot. Let me know if you have any questions, but you will end up with very similar answers on the lab analysis questions. So if that's happening, don't worry, it's not wrong. You do just have a lot of similar scenarios here happening. So there's that, and then you guys do have a couple of practice questions that go along with this that are related to scenarios like this. Keep in mind that if you had two forces running head-on into each other, you would double these forces in these equations here. So that's about it. So please give those a shot. Let me know if you have any questions, and I will talk to you guys next time.